We've discussed the Dyna architecture and how it combines planning, learning, and acting. We have also studied how Dyna Q operates in a grid world. Let's get down to business and run some experiments to see how well Dyna Q really works. In this video, you will use a small grid world to compare tabular Dyna Q and model-free Q-learning. By the end of this video, you will be able to describe how learning from both real and model experience impacts performance. You will also be able to explain how a model allows the agent to learn from fewer interactions with the environment. Today, we will run some experiments on this small maze environment. Like before, the agent has 4 actions. Transitioning into the goal state generates a reward of +1. All other transitions generate a reward of 0. This problem is episodic, and we will use a discount of 0.95. Let's compare Dyna Q with different amounts of planning. We will compare 3 agents. Each one will use alpha equal to 0.1 and epsilon equal to 0.1. We initialize the action value estimates to 0 for all 3 agents. We ran the experiment for 50 episodes 30 times and then averaged the results. Let's have a look. We can plot the average number of steps the agent took to complete each episode after more and more episodes. If the agent is doing well, then the number of steps should decrease with more episodes. That is, lower on the y-axis is better. If we run Dyna Q with 0 planning steps, we get exactly the Q-learning algorithm. As we can see, it slowly gets better, but plateaus at around 14 steps per episode. If we run Dyna Q with 5 planning steps, it reaches the same performance as Q-learning, but much more quickly. Dyna Q with 50 planning steps only takes about 3 episodes to find a good policy. Dyna Q is far more sample efficient. Look at the y-axis. After 2 episodes, the policy found by Q-learning still requires hundreds of steps to escape the maze. For the same number of environment interactions, Dyna Q can learn a lot more. This shows how planning makes better use of environment experience if the model is correct. Let's visualize what's going on in a slightly different maze. We use an arrow to show the greedy action according to the estimated value in each state. A state without an arrow means that every action is equally likely under the policy. After 1 episode, Q-learning updates just 1 action value, the one corresponding to the up action in the state next to the goal. This is the only state where a transition with the non-zero reward was experienced. It would take several more episodes to bootstrap this state's value back to other nearby states. Let's look more closely at how search control impacts planning. Our robot will do things slightly differently than Dyna Q, but that's just to emphasize our point more clearly. We will start with 10 planning steps and call the planning loop 10 times in a row. So that's 100 steps of planning in total. As you can see, many of the planning updates fail to change the value function. In fact, the agent only updated the values of 2 state action pairs after 100 steps of planning. Let's keep going. This time, we will try 100 planning steps per call and let the agent run a bit longer. Even with the 100 planning steps, the first few calls update only a handful of action values. Why does the agent need so many planning steps to learn the value function and a reasonable policy? The agent needs many planning steps because search control samples state action pairs randomly. The planning update will not have any effect if the sampled state action pair produces a 0 TD error. This happened a lot in this environment because all the rewards are 0, and so are the initial values. What would happen if we ordered the state action pairs in a more efficient way? It turns out the agent could learn a good policy only using 1/6 of the planning updates. In large environments, random search control becomes even more problematic. If you want to learn more about this topic, check out section 8.4 of the textbook. In this video, we tested the tabular Dyna Q algorithm in a simple grid world. We saw how planning can dramatically speed up learning. In our experiment, the more planning we did, the better the agent performed. Bye for now.